Please subscribe to support the channel. The idea of traveling at the speed of light is not just a simple what-if question, it's a doorway into one of the most fascinating corners of physics. It sits at the crossroads of curiosity, imagination, and hard scientific law. The reason this thought experiment is so intriguing is that it pushes us to confront the limits of what is possible. Human beings are explorers by nature. We look at oceans. We cross them. We look at mountains. We climb them. We look at space, and we build rockets to touch the stars. So, naturally, when we learn that light, the fastest thing in the universe, moves at a speed we can hardly comprehend, the next question is inevitable. What if we could ride alongside it? But before going further, we need to face a sobering truth. Physics tells us something very clear. Nothing with mass can ever truly reach the speed of light. It's not like a speed limit on a highway that can be broken with a faster car. It's more like a wall of reality itself, a barrier that no material object can pass through. This impossibility doesn't mean we shouldn't think about it, though. In fact, the impossibility is what makes the question so interesting. Because by stretching our imagination into that forbidden territory, we get to uncover insights about energy, time, space, and how the universe itself operates. Think of it as a mental simulation. Just as scientists use particle accelerators to push tiny subatomic particles near the speed of light to study their behavior, we can use this thought experiment as a way of accelerating our own minds. We are asking, if the universe did allow us to break its biggest rule, what strange and extraordinary experiences would unfold? In this kind of thought experiment, you have to suspend disbelief while still respecting the scientific framework. You're not literally saying we can strap a rocket to a spaceship and make it hit light speed. Instead, you're saying, what would the universe look like from that perspective? It's like climbing into the shoes of a photon, one of the particles of light itself, and seeing the cosmos the way it does. And here's the beauty of it. While we know light speed travel is impossible for humans, the consequences of even approaching that speed are very real and measurable. Astronauts on the International Space Station already experience tiny amounts of time dilation, time running just a little bit slower for them compared to us on Earth, because they're moving quickly relative to us. Particle physicists routinely accelerate protons and electrons to a fraction below light speed and watch them behave exactly as Einstein predicted. So, while the exact thought experiment of moving at light speed is impossible, the surrounding physics is not only possible but confirmed again and again in labs all over the world. That's what makes this exploration so rich. It's fiction rooted in fact, imagination tied to mathematics. It's not about whether we can actually travel at light speed. It's about using the idea to peel back the curtain on how reality really works. And once you start pulling on that thread, you discover that the universe is far stranger and more beautiful than common sense ever led us to believe. The speed of light is one of those numbers that seems straightforward when you first hear it, but the moment you actually sit with it, the scale becomes almost incomprehensible. Light travels at 299,792 kilometers every single second. That's about 186,282 miles in just one heartbeat of time. To put that into perspective, think about the Earth itself. The circumference of our planet is roughly 40,000 kilometers. Light could circle around the entire Earth more than 7 times in a single second. 7 laps around the world, done before you could even blink. That speed is not just fast in a human sense, it is so far beyond our daily experience that even when we throw analogies at it, we still don't really feel it. Let's bring it closer to home. Imagine a passenger jet flying at cruising speed, say about 900 kilometers per hour. At that pace, it would take you about 45 hours to travel once around the globe. Now stack that against light, which does that trip 7 times every second. The gap is so enormous that it doesn't even feel like a comparison anymore. It's like trying to compare the size of an ant to the size of the entire planet. Both numbers technically live in the same universe, but one dwarfs the other so completely that it stretches the imagination just to put them side by side. The Moon is about 384,000 kilometers away from Earth. At ordinary rocket speeds, it takes astronauts roughly 3 days to cover that distance. Light does it in about 1¼ seconds. Think about that. Every time you see the Moon shining above you, the light that left its surface arrived in just over a single second. The Sun, much farther away at 150 million kilometers, provides another staggering example. Light leaving the surface of the sun takes about 8 minutes and 20 seconds to reach Earth. So when you step outside and feel the warmth of sunlight on your skin, you are literally experiencing the sun as it was more than 8 minutes ago. In a sense, we're always looking into the past when we look into the sky. Now push further out into the cosmos. The nearest star system to us, Alpha Centauri, sits about 4.37 light-years away. That means even at light speed, traveling non-stop, it would take more than 4 years to reach it. Our fastest spacecraft, like the Parker Solar Probe or Voyager 1, crawl along at tens of kilometers per second, nowhere near light speed. At those speeds, it would take tens of thousands of years to get to Alpha Centauri. Light slices through that gap in just over 4 years, a blink compared to cosmic timescales. And when astronomers talk about galaxies billions of light-years away, that number carries profound meaning. Light from those galaxies has been traveling for billions of years to reach us. We are literally seeing them not as they are now, but as they were when dinosaurs walked the Earth, or even long before our planet formed. Light speed doesn't just define how fast information moves, it defines how we perceive reality itself. It is the universal frame of reference for how we connect with the cosmos. What's astonishing is that this incredible speed is the same everywhere, no matter where you are or how fast you're moving. Whether you're standing still on Earth, riding in a rocket at a significant fraction of light speed, or watching photons zip through a vacuum in deep space, the number is always the same: 299,792 kilometers per second. This invariance is one of the cornerstones of modern physics and one of the reasons Einstein developed his theory of relativity. The constancy of light speed is not just a number on a chart, it is a fundamental feature of the universe, something that space and time themselves bend around. If you want another way to think about just how fast light travels, picture this. Suppose you had a flashlight powerful enough to shine its beam toward Mars when it's at its closest distance to Earth, which is around 54 million kilometers. The light would reach Mars in about 3 minutes. Even signals we send to spacecraft, radio waves, which also move at the speed of light, take minutes or hours to travel between planets. This is why engineers communicating with rovers on Mars have to wait for instructions to arrive and then wait again for a response. Even light, the fastest messenger in existence, struggles when distances stretch across the solar system. Here's another mind-bending scenario. If you could somehow build a road from the Earth to the Sun and drive at highway speeds, let's say 100 kilometers per hour, it would take you over 170 years of non-stop driving to make the journey. Light makes that same trip in just over 8 minutes. The difference is so large that it makes human concepts of speed feel almost trivial. In a sense, light isn't just fast. It's a benchmark against which everything else looks almost frozen in comparison. This number, 299,792 kilometers per second, shows up everywhere in physics. It's not just how fast light moves, it's also the maximum speed at which information can travel, the ultimate limit woven into the fabric of reality. It is the speed at which cause and effect propagate, the speed at which the ripples of the universe carry knowledge of what just happened to the next place. In fact, the very structure of spacetime is defined by this limit. If you could somehow break it, you wouldn't just be moving faster, you'd be stepping outside of the order of time itself. It's important to pause here and remember that this number isn't arbitrary. It emerges from the very laws of nature. The universe itself has decided, in its most fundamental design, that 299,792 kilometers per second is the maximum. When physicists use the equations of relativity, the speed of light, represented as c, isn't just a speed. It's a constant that acts as the scaffolding for the entire system. It shows up in formulas that describe energy, like the famous E equals mc squared. It shows up in equations for electromagnetism, where it links electric and magnetic fields. It shows up in quantum mechanics, where it defines how particles interact. In short, it is not just a number, it is the heartbeat of the universe. And here's the paradox. While it is unimaginably fast, in the context of the cosmos, it is also painfully slow. When we talk about stars that are millions or billions of light-years away, it means even light, moving at its incredible speed, struggles to bridge the vastness of space. The universe is so large that the fastest thing in existence still takes eons to cross it. This duality, light being both the fastest and yet insufficient to make the cosmos feel small, is one of the most humbling truths in science. When we start thinking about what happens as you approach the speed of light, we immediately step into the territory of one of the greatest revolutions in science, Einstein's theory of special relativity. This isn't just another physics theory sitting on a shelf somewhere. It's the very framework that reshaped our understanding of time, space, and reality itself. Before Einstein, people thought of time as absolute, ticking away like a universal clock that was the same for everyone everywhere. They thought of space as a fixed stage, a backdrop where the events of the universe played out without being influenced by what happened within it. But in 1905, Albert Einstein tore down those assumptions with an idea that was both elegant and unsettling. The laws of physics are the same for all observers, and the speed of light is constant for everyone, no matter how fast they are moving. To appreciate how shocking this was, imagine yourself sitting in a car. If you're driving at 100 km per hour and you toss a ball forward at 20 km per hour, someone standing on the sidewalk would see the ball moving at 120 km per hour relative to them. Speeds add up in our everyday world. But light doesn't work that way. If you turn on your car's headlights while driving, you might think the beam of light should move at the speed of light plus your car's speed relative to the sidewalk. But that's not what happens. No matter how fast you're going, no matter who is watching, the beam of light always races ahead at exactly 299,792 km per second. It never adds, never subtracts, it's constant. This is the strange rule of the universe that Einstein placed at the heart of special relativity. And here's where things get wild. If the speed of light is constant for everyone, then something else has to give. What bends and flexes to preserve that constancy is not the light, it's time and space themselves. To make sure no one ever measures light going faster or slower, the universe plays with the variables of reality. Time slows down. Lengths contract. Simultaneity, the idea that two events happen at the same time, breaks apart depending on your frame of reference. These effects aren't illusions, they are the real consequences of moving close to light speed. Think about what this means. Suppose two observers, one standing still on Earth and another zipping through space at near light speed, both measure the speed of light. They will get the exact same number, even though one of them is moving incredibly fast. For that to be true, the universe must literally warp the way time flows and the way distances appear to each observer. This is why special relativity isn't just a small tweak to Newton's old laws of motion. It's a complete rewriting of the rules for reality when speeds become extreme. One of the most important outcomes of this theory is the realization that space and time are not separate entities. Instead, they are part of a single, interconnected fabric called spacetime. When you move faster through space, you experience less passage through time. Conversely, when you are still in space, you move more quickly through time. In other words, there's a kind of trade-off. The faster you travel through space, the slower your clock runs compared to someone standing still. This link between space and time is the foundation for all the bizarre but real phenomena that happen as you approach light speed. Another revolutionary aspect of special relativity is that it doesn't just deal with motion, it connects directly to energy and mass. This is where Einstein's most famous equation, E equals mc squared, comes in. It tells us that energy and mass are two sides of the same coin, interchangeable forms of reality. A small amount of mass contains an enormous amount of energy because it is multiplied by the square of the speed of light. And since the speed of light is such a huge number, the energy bound up in matter is staggering. That's why nuclear reactions release so much power. They're tapping into the mass-energy equivalence at the heart of relativity. But for our thought experiment, the key point is that relativity lays out why strange things happen as we approach the speed of light. It explains why your mass seems to increase, why time slows down, why distances shrink, and why communication becomes impossible at such speeds. None of these are guesses. They are the logical consequences of Einstein's postulates, and they have been proven countless times in experiments, from particle accelerators to atomic clocks flown on airplanes. So when we talk about traveling at light speed, what we're really doing is stepping into Einstein's playground. We're testing the limits of space-time itself, following the rules he discovered, and seeing what happens when we push them to their extremes. It's the reason we can't just think about light speed in terms of faster engines or better rockets. The barrier is not engineering, it is physics at the most fundamental level. The universe has built-in rules, and relativity is the rulebook. As we continue this journey deeper into the strange territory of near-light speed travel, we now come to one of the most mind-bending consequences of Einstein's theory, the phenomenon of mass increase. This concept, sometimes called relativistic mass, tells us that the faster you move through space, the heavier you effectively become. Not heavier in the sense that you would feel like you're carrying extra weight if you stepped on a scale, but heavier in the way the universe treats your resistance to acceleration. It's as though, the closer you push toward the cosmic speed limit, the more stubbornly the universe pushes back, refusing to let you cross the finish line. To unpack this, let's start with something more familiar. When you push a shopping cart at the grocery store, you apply a certain force, and the cart accelerates forward. The relationship between force, mass, and acceleration was famously described by Isaac Newton in his second law. Force equals mass times acceleration. The bigger the mass, the more force you need to accelerate it. Pushing an empty cart is easy. Pushing a cart loaded with bottled water is much harder. That's everyday Newtonian physics. Now, apply that same logic to an object moving close to light speed. In the Newtonian view, if you just kept pushing, you could accelerate an object indefinitely. There's no built-in speed limit. But in Einstein's relativistic world, the rules change dramatically. The closer you get to the speed of light, the more your effective mass increases. What does this mean? It means that your resistance to acceleration grows, not because your actual atoms are getting heavier, but because from the perspective of the physics equations, your energy and momentum start behaving as though you're more massive. You could pour more and more energy into accelerating, and you would keep going faster, but at an ever-slowing rate of increase. Your speed creeps closer and closer to light speed, but never reaches it. To see why this happens, we need to look at how relativity describes energy and momentum. At everyday speeds, energy is given by the familiar formula E equals 1/2 mv squared. But as you move closer to light speed, that simple formula no longer works. Instead, relativity tells us that the total energy of an object is given by E equals mc squared, where m is the rest mass, c is the speed of light, and gamma is a factor that grows larger and larger the closer you approach light speed. Gamma is defined as 1 divided by the square root of 1 v squared c squared, where v is your velocity. That denominator, 1 minus v squared c squared, is the key. If your speed v is much smaller than c, then v squared c squared is a tiny number, and gamma is essentially 1. In that case, the formula reduces to the familiar Newtonian energy. But as your speed v gets closer to c, the denominator shrinks towards 0, and gamma grows without limit. This means that your energy skyrockets as you get faster. And since mass and energy are equivalent, it also means your effective mass skyrockets. At 90% of light speed, your relativistic mass is about 2.3 times your rest mass. At 99% of light speed, it's about 7 times greater. At 99.9%, it's about 22 times greater. At 99.9999%, the numbers become staggering, hundreds, thousands, millions of times more massive. And as you asymptotically approach 100%, true light speed, your mass effectively becomes infinite. To accelerate something with infinite mass, you would need infinite energy. And since there is no such thing as infinite energy in the universe, the conclusion is inescapable. Nothing with mass can ever reach the speed of light. Let's bring this down to an example. Imagine trying to accelerate a spaceship. At first, when it's moving relatively slowly, every bit of energy you pour into the engines translates efficiently into speed. But as you start approaching 50% or 70% or 90% of light speed, the returns diminish. You pour in the same amount of energy, but the speed increases less and less. Your engines are still burning, but instead of gaining much speed, the energy goes into increasing your relativistic mass. It's like trying to run uphill and discovering that the hill gets steeper and steeper the faster you go. At some point, no matter how much fuel you burn, you can't make it up the slope. The slope becomes vertical, and you are stuck just shy of the top. That top is light speed, and the vertical climb is the need for infinite energy. This concept isn't just theoretical, it's observed in particle accelerators. At facilities like CERN's Large Hadron Collider, scientists accelerate protons to speeds incredibly close to light. These protons don't quite reach the speed of light, but they gain massive amounts of energy. In fact, They become so energetic that their relativistic mass is thousands of times greater than their rest mass. Yet even with the enormous power of the collider, the particles never cross the light speed barrier. They skim closer and closer but are forever barred from reaching it. This isn't a limitation of our machines. It's a limitation imposed by the universe itself. There's also a fascinating twist to this. While mass seems to increase with speed, it's important to remember that from the perspective of the moving object itself, say, from the point of view of a traveler inside the spaceship, you don't feel heavier. You still feel like you have the same mass. It's only from the perspective of an outside observer that your resistance to acceleration grows and your mass appears to balloon. This highlights the deeply relative nature of Einstein's physics. Different observers can see the same reality in profoundly different ways, and both can be correct within their own frame of reference. When you really sit with this concept, it becomes clear that the impossibility of light-speed travel isn't some arbitrary barrier. It's not that the universe is being stingy or unfair. It's that the very structure of space, time, and energy creates a horizon you can never cross. Just like you can never divide by zero in mathematics, you can never accelerate a mass to light speed in physics. It's a kind of cosmic protection built into the equations themselves. And it has profound implications. It means that our dreams of jumping instantly across the galaxy are not simply a matter of better technology. They run up against the actual laws of the universe. Unless we discover entirely new physics that goes beyond relativity, something that would rewrite our understanding of reality itself, we are bound by this speed limit. For now, and for all the foreseeable future, light speed is not a destination, but a wall. This concept of mass increase is a sobering reminder that our intuitions, shaped by the slow speeds of everyday life, don't apply when we start dealing with the extreme edges of reality. At ordinary speeds, we never notice this effect because it's so small. Driving at 100 km per hour doesn't increase your mass in any measurable way. But push closer and closer to the ultimate limit, and the strangeness of relativity begins to dominate. It's like stepping into a world where the rules we thought we knew no longer work, and the deeper truth of the universe is revealed. Time dilation is one of those ideas that completely rewires the way you think about reality. At first, it sounds like pure science fiction. Time slowing down for one person while another continues normally. But it isn't a fantasy. It's a direct consequence of Einstein's special relativity and one of the most well-tested predictions in all of physics. To say that time dilation is real is not just a claim, it's something we've measured again and again with extreme precision. And when you begin to understand what it means, it changes the way you look at your own existence. At the heart of time dilation is a simple principle. The speed of light is constant for all observers. We touched on this earlier. No matter how fast you're moving, if you measure the speed of light, you'll always get 299,792 kilometers per second. For this to hold true across all perspectives, the universe has to adjust something else to make the math balance. That something else is the flow of time. When you move faster and faster through space, your personal time, what physicists call your proper time, runs slower compared to someone who is standing still. Here's an analogy to make this more intuitive. Imagine space-time as a kind of grid, where every object is moving through both space and time. If you're sitting still in space, you're moving forward only through time. If you're moving quickly through space, then less of your motion is available to move through time. There's a kind of trade-off. The faster you go through space, the slower you go through time. From your perspective, everything feels normal. Your heart beats, your thoughts occur, your watch ticks at its usual pace. But from the perspective of someone watching you from a stationary frame, everything about you appears slowed down. To see how dramatic this can be, let's look at some numbers. At everyday speeds, say, driving a car at 100 km per hour, the effect of time dilation is negligible. You would never notice it. But as you approach a significant fraction of the speed of light, the effect becomes impossible to ignore. At 90% of the speed of light, time for you would slow down by about a factor of 2.3. That means if you took a trip lasting 1 year by your onboard clock, more than 2 years would pass for someone back on Earth. At 99% of the speed of light, the factor is about 7. If you traveled for 1 year, 7 years would pass back home. Push to 99.9% and the factor becomes 22. 1 year for you, 22 for the Earth. And as you get closer and closer to light speed, the dilation grows without bound. What this tells us is that moving at relativistic speeds is not just about going fast, it's about stepping into a different relationship with time itself. It's not simply that your watch looks like it's running slow to an outside observer, it is running slow relative to them. Time is not absolute, not a universal rhythm beating across the cosmos. Instead, time is flexible, personal, relative to your motion. This isn't just theory, it has been proven with experiments. One of the most famous involved taking extremely precise atomic clocks and flying them on airplanes around the Earth. When compared with identical clocks left on the ground, the airborne clocks ticked more slowly, exactly as relativity predicted. Another piece of evidence comes from high-energy particles called muons, which are created when cosmic rays strike the upper atmosphere. Muons are unstable, with a very short lifetime. If they were traveling according to classical physics, they would decay long before reaching the ground. But because they are moving close to light speed, their internal clocks are slowed down, allowing many of them to survive the trip all the way to Earth's surface. Their existence here is proof of time dilation happening naturally in the sky above us. Time dilation is also an everyday concern for modern technology. The GPS system that guides airplanes, cars, and smartphones has to account for both special relativity and general relativity, which deals with gravity's effect on time. Satellites orbiting Earth are moving fast enough and are in a weaker gravitational field compared to the surface, so their onboard clocks tick at a slightly different rate than clocks on Earth. Engineers must correct for this difference, or else GPS would accumulate errors of kilometers within a single day. The fact that your phone can navigate to the nearest cafe is thanks to relativity, and the reality of time dilation. But beyond the experiments and technology, what makes time dilation so breathtaking is what it means for human experience. Imagine being an astronaut who boards a near-light-speed spacecraft. You travel for what feels like a few years. Maybe you journey to a distant star and back. When you return, you step out of your ship to find that decades, or even centuries, have passed on Earth. Your siblings, your friends, your entire society may have grown old or even vanished, while you experienced only a handful of years. For you, the trip was perfectly ordinary. For those left behind, your absence spanned lifetimes. This leads to one of the most famous thought experiments in physics, the twin paradox. Imagine two twins, one of whom stays on Earth while the other boards a spaceship traveling close to the speed of light. The traveling twin experiences time dilation, so when they reunite, the spacefaring twin is younger than their sibling. This isn't a paradox in the sense of a contradiction. It's a paradox only because it defies our everyday intuition. The explanation is that the traveling twin underwent acceleration and deceleration, changing reference frames, while the Earth twin did not. The math of relativity handles it perfectly, and experiments confirm it. What's perhaps most profound about time dilation is that it shows us how flexible reality is. We grow up with the sense that time is this unchangeable, relentless river that carries everything along equally. Relativity reveals that time is more like a fabric, stretching and shrinking depending on how you move through the universe. If you go fast enough, you can effectively step into the future, skipping over centuries in the blink of an eye from your own perspective. The laws of physics don't forbid it, they demand it. And yet, time dilation also highlights the bittersweet limits of our dreams. It makes interstellar travel theoretically possible within a single lifetime, because your personal clock could run slower than the galaxies. But it also means that the world you leave behind will not wait for you. You could cross incredible distances, but you would pay with the price of separation from everything familiar. Time dilation is both a gift and a barrier, a doorway into the future and a reminder of the deep personal consequences of relativity. Let's anchor the abstract concept of time dilation into something personal and relatable, something that paints a vivid picture of what it would actually feel like if humans could approach the speed of light. Imagine an astronaut preparing for an extraordinary mission, one unlike anything humanity has ever attempted. She boards a spacecraft capable of traveling at 99.9% of the speed of light. To her, the ship feels perfectly ordinary. The engines fire, she feels the vibration of acceleration, and once she's cruising at relativistic speeds, life inside the cabin seems calm and familiar. Her watch ticks second by second, her heart beats rhythmically, her body experiences time just as it always has. She sets out on a mission that, by her own onboard clock, will last 1 year before she returns home to Earth. But here's the twist. While that 1 year passes for her, far more time passes for the people she left behind on Earth. At 99.9% of light speed, the time dilation factor, what physicists call the Lorentz factor, is about 22. That means for every single second she experiences on her ship, 22 seconds pass on Earth. For every hour in her spacecraft, nearly a full day races by back home. For every day she spends aboard her vessel, about 3 weeks slip by on Earth. When she finally completes her 1-year journey and returns, she steps out of her ship to discover that 22 years have passed on Earth. Her single year of adventure has cost her 2 decades of Earth time. Picture the reunion. For her, it feels as though she just said goodbye to her loved ones, but for them, it's been an entire generation. Her friends have aged. Her younger brother is now in his 40s. Her parents may have passed away. Technology has advanced. The world she once knew has changed into something unfamiliar. She's been gone for what feels like a blink, but her absence was nearly a lifetime for everyone else. This is not hypothetical hand-waving. This is what relativity predicts, and it has been tested again and again in particle physics experiments. When scientists accelerate unstable particles to near-light speeds, those particles live much longer than they would if they were at rest. Their internal clocks slow down relative to ours. The astronaut in our thought experiment is no different. Her biological processes slow relative to those of people back on Earth. To her, everything is normal. To Earth, she's moving through time in slow motion. Now let's scale it even further. Suppose instead of 99.9% of the speed of light, her spacecraft reaches 99.999999% of light speed, a velocity achievable only in theory, but one that illustrates the extreme nature of time dilation. At that speed, the dilation factor is about 7,000. If she traveled for 1 year by her watch, nearly 7,000 years would pass on Earth. She could set out in the early 21st century, return what feels like a year later, and find herself in the year 9000 AD. Civilizations would have risen and fallen, languages would have transformed, continents might even look different. From her perspective, she simply took a brief sabbatical. From Earth's perspective, she became a visitor from the distant past. It's this dramatic disparity that makes time dilation so hauntingly fascinating. It allows us to think seriously about the possibility of time travel to the future. Not in the sense of stepping into a machine and instantly leaping forward, but by moving so quickly that your personal experience of time slows down compared to the rest of the universe. The astronaut doesn't need a time machine. Her ship is the time machine, built out of the very laws of physics. And this isn't just about mathematics, it's about the deeply human side of the story. Imagine being that astronaut, sitting in her spacecraft as stars streak faintly around her. She knows intellectually that decades are flying by back home with every month she spends in space, but emotionally, it feels impossible. For her, birthdays, meals, and daily routines continue with their usual rhythm. How strange would it feel to write a letter before launch and then, upon returning, discover that the person she wrote it to had grown old, perhaps even died, while she remained almost unchanged? Science fiction often plays with this theme because it strikes such a powerful chord. Films and novels depict explorers who return home to find a world transformed by centuries of history. It's dramatic, yes, but it's also rooted in the real physics of relativity. The astronaut's journey is a real consequence of how time works at high speeds. What makes it even more remarkable is that this effect doesn't require magical technology. It's already happening, albeit on much smaller scales. Astronauts aboard the International Space Station orbit Earth at about 27,000 kilometers per hour. That's fast enough that time dilation affects them very slightly. Each astronaut experiences a tiny fraction of a second less than people on Earth over the course of a 6-month mission. It's not dramatic enough to notice, but it's there, measurable, and completely in line with Einstein's predictions. Our hypothetical astronaut is simply stretching that tiny difference into something world-changing. This example makes one thing absolutely clear: time is not universal. It's not a single drumbeat that everything follows. It's personal, relative, shaped by your motion through the cosmos. And when you move close to the ultimate speed limit, you step into a reality where the ordinary flow of time splinters into separate experiences. The astronaut's year and the Earth's decades are equally real, equally valid, but radically different. Length contraction is the perfect companion to time dilation. It's the other half of the strange bargain the universe makes when you move close to the speed of light. If time slows down for the traveler compared to the outside world, then space itself also reshapes to make the equations balance. From the perspective of the person moving at relativistic speeds, distances in the direction of travel literally shrink. The universe becomes compressed, squashed down along the axis of motion, as though the cosmos is folding itself up to accommodate the traveler's extreme speed. This is another unavoidable consequence of Einstein's relativity. Remember, the speed of light must remain constant for all observers. To make this work, not only does time stretch and bend, but space itself has to flex as well. Length contraction, sometimes called Lorentz contraction, describes exactly how this happens. The formula is straightforward. The contracted length L is equal to the proper length L, the distance measured by someone at rest, multiplied by the square root of 1 v squared c squared. That square root term is the same factor we saw in time dilation, only now it affects distances rather than clocks. So what does this mean in practice? Suppose you're an astronaut traveling toward a distant star 10 light-years away. To someone on Earth, that star really is 10 light-years distant. If you travel at 90% of light speed, it will take you about 11 years to get there in Earth's frame of reference, because the trip covers 10 light-years and you're going just under light speed. But from your perspective inside the spacecraft, things look very different. At 90% of light speed, distances along your direction of motion shrink by a factor of about 0.44. That means the 10 light-year distance is reduced to just 4.4 light-years. Traveling at 90% of light speed, you can cross that contracted distance in under 5 years by your own clock. Push your velocity to 99% of the speed of light, and the effect becomes even more dramatic. The contraction factor drops to about 0.14, so the 10 light-year trip now looks like 1.4 light-years to you. At that speed, your journey feels like it takes only 1.4 years, even though Earth observers record a full 10 years passing. The faster you go, the smaller the universe becomes. From your frame of reference, space compresses so much that the impossible distances of the cosmos suddenly look achievable. Now consider the extreme case of 99.999999% of light speed. At this velocity, the contraction factor is vanishingly small, on the order of 0.0014. The 10 light-year distance shrinks down to a mere 0.014 light-years, which is about 5 light days. For you, the traveler, the star feels just days away, while Earth observers watch you take a full decade to arrive. This is the breathtaking power of length contraction. What looks impossibly far from Earth becomes startlingly close when you're racing near light speed. It's important to emphasize that this isn't an illusion or a trick of perception. The distance genuinely is shorter from your frame of reference. Relativity doesn't deal in illusions. It deals in realities that are relative to observers. In your spaceship, rulers would measure shorter, the star would genuinely be closer, and your journey would genuinely take less time by your clock. Meanwhile, Earth observers are equally correct in saying that you took the long way and required years or decades. Both viewpoints are true, and the laws of physics accommodate both without contradiction. This effect is so strange because it clashes with our everyday intuition. Distances feel fixed to us. If a mountain is 10 kilometers away, it's 10 kilometers away for everyone. We don't expect the act of moving to change the mountain's distance. But relativity forces us to let go of that intuition. The structure of space itself bends to keep light speed constant, and what we think of as rigid, unchanging distances are actually malleable when you move fast enough. Imagine again our astronaut, zipping toward a faraway galaxy. From Earth's perspective, the galaxy might be millions of light-years away, an unreachable horizon for human lifetimes. But to the astronaut traveling at extreme speeds, length contraction would compress that mind-boggling gulf of space into something traversable within a single lifetime. She could leave Earth, race toward a distant galaxy, and arrive after a few decades of her own time, even if billions of years passed outside her frame. Length contraction turns impossibility into possibility, but at the price of severing the traveler's timeline from everyone else's. There's a deeply poetic side to this. It means that the universe is not fixed and immutable. It's flexible, alive, and deeply personal. What you see as vast and insurmountable may be shrunk to a manageable size for someone else, depending on their motion. The cosmos isn't a single, objective stage. It's a shifting, relative experience that depends on how you move through it. And just like with time dilation, we've already confirmed length contraction in experiments. Particle accelerators again provide the proof. High-energy protons traveling near light speed see the world compressed in the direction of their motion. To these protons, the length of the accelerator ring appears much shorter than it does to engineers building the machine. This contraction is precisely what allows them to complete laps at near-light speed in a way that matches Einstein's predictions. If you stop and think about it, length contraction is what makes interstellar dreams at least mathematically conceivable. For Earthbound observers, the nearest galaxies are millions of light-years away, forever beyond our reach. But for travelers approaching light speed, those same galaxies contract to far more approachable distances. They could, in principle, cross the cosmos in what feels like a human lifetime. The catch, of course, is that when they look back, billions of years may have passed in the rest of the universe. Length contraction, then, is both exhilarating and sobering. It opens doors to possibilities that our Newtonian minds never imagined, but it also reminds us of the high price of relativistic travel. The faster you go, the smaller the universe becomes, but also the more disconnected you become from the time and reality you left behind. If time dilation and length contraction already feel like the universe rewriting its own rules, then the question of what you would see at near-light speed adds another layer of strangeness. Vision is nothing more than the process of detecting light. Photons bounce off objects, travel across space, and enter your eyes, where your brain processes them into a picture of reality. But when you're traveling at a significant fraction of the speed of light, the very light entering your eyes is distorted by your motion. The cosmos itself appears warped, colors shift dramatically, and parts of the universe even vanish from view. To understand this, we need to talk about the Doppler effect. You've almost certainly experienced it before. Imagine standing on a sidewalk as an ambulance races past. As it approaches, the siren's pitch sounds higher. As it passes and moves away, the pitch drops lower. That change in pitch is due to the compression and stretching of sound waves caused by motion. The same thing happens with light waves, it's just that instead of changing pitch, the color of the light shifts. This is known as the relativistic Doppler effect. When you're racing toward a source of light, the wavelengths of those photons get compressed. Compressed light means shorter wavelengths, and shorter wavelengths shift toward the blue end of the spectrum. This is called blue shift. The faster you move, the more the starlight ahead of you gets pushed toward blue and eventually into ultraviolet or even X-ray frequencies, ranges invisible to the human eye but not to instruments. To your eyes, stars ahead of your spacecraft would first look dazzlingly blue-white, then fade into invisibility as their radiation shifts beyond what you can perceive. On the other hand, the stars behind you stretch out. Their light waves elongate, moving toward longer wavelengths. This is called redshift. Stars that would normally glow white or yellow get stretched into deep crimson, then into infrared, and eventually into radio waves, again, completely invisible to human eyes. From your perspective, the stars behind you would dim, redden, and then disappear altogether. The result is that your visual field collapses. Instead of seeing stars surrounding you in all directions, you would see most of them compressed into a bright, blinding oval ahead of you, while the rear of the universe fades into darkness. It's as though the cosmos funnels forward, squeezing the night sky into a tunnel of distorted starlight. Physicists call this phenomenon relativistic aberration. Because you're moving so fast, the apparent direction of incoming light skews. Even light from stars at your sides gets bent into the forward field of view. The faster you go, the narrower your vision becomes, until at near-light speeds, everything seems concentrated into a glowing spot directly ahead. This is not speculation, it's the unavoidable consequence of relativity. Imagine turning on your headlights while driving close to light speed. To you, the photons leaving your lamps still move outward at light speed, but because of the distortions of space and time, they bunch up ahead. To an outside observer, those photons may appear stretched and skewed, but to you, the forward path becomes blindingly bright. If your ship didn't have shielding, the starlight compressed into ultraviolet and X-ray radiation would bombard you like a constant flood of cosmic rays. In other words, The very act of moving close to light speed transforms ordinary starlight into hazardous radiation. The beauty of this thought experiment is that it lets us imagine what a relativistic journey would feel like visually. Picture sitting in the cockpit of your spacecraft. At first, as you accelerate to a fraction of light speed, the stars begin to shimmer strangely. Ahead, they grow brighter, shifting toward blue. Behind, they fade into red. Push faster, and the oval of forward starlight tightens, concentrating into what looks like a tunnel. By the time you're at 99% of light speed, the universe has collapsed into a luminous cone ahead of you, while the rest of the sky is swallowed by darkness. Push closer still, and most of that light has shifted into invisible wavelengths. To your naked eye, you might be flying into a black void, with only the faintest flickers of radiation instruments could detect. It's fascinating to think that at extreme speeds, the very concept of a star-filled sky vanishes. The constellations you grew up with would distort beyond recognition. Orion's belt would collapse inward, the Big Dipper would stretch and warp, and eventually, no familiar patterns would remain. The night sky would stop being a comforting dome of light and instead become an alien, compressed glow ahead of you. The universe would feel smaller, harsher, and far stranger. And it's not just visual beauty at stake, it's survival. At relativistic speeds, the blue-shifted photons ahead carry tremendous energy. Cosmic microwave background radiation, the faint afterglow of the Big Bang, fills the universe in every direction. Normally, it's harmless, sitting at microwave frequencies. But at near-light speed, that radiation blue shifts into dangerous ranges. For a traveler, the universe itself becomes a deadly flood of high-energy photons and particles. The faster you go, the more hazardous the environment becomes. This is one of the many biological challenges we'll return to later. But let's pause on the visual side for a moment, because there's something profoundly humbling about it. Our sense of beauty in the night sky is rooted in the idea of a stable, eternal tapestry of stars. Yet relativity reveals that this tapestry is fragile, shifting, and personal. At ordinary speeds, we all agree on what the sky looks like. At relativistic speeds, no two observers see the same universe. The cosmos we think of as fixed is, in fact, malleable, shaped by motion. To the astronaut approaching light speed, the universe doesn't look infinite anymore. It looks like it's collapsing inward, folding into a tunnel of distorted light. The comforting familiarity of space becomes a disorienting storm of radiation. And perhaps most hauntingly, if she could actually reach the speed of light, which we know is impossible, no light from ahead could ever reach her eyes in the normal way. The forward cosmos would vanish completely, leaving her in a strange, lightless silence. That scenario leads directly into the next idea, the so-called light wall. As we take the next step into the extreme edge of physics, we encounter a truly mind-bending scenario, the so-called light wall. This is what happens when you try to imagine traveling not just near the speed of light, but actually reaching it, a hypothetical boundary that no object with mass can cross. While special relativity forbids this in practice, contemplating it gives profound insight into how the universe fundamentally operates. At everyday speeds, light moves freely around us. We see stars, sunlight streams in through windows, and photons bounce off objects to form the images our eyes process. But as we approach light speed, the very behavior of incoming light begins to warp in extreme ways. Relativistic effects like Doppler shifting and aberration compress most of the observable universe into a bright, forward-facing cone. The stars ahead become blue-shifted, those behind red-shifted, and the field of view narrows into an intense tunnel. The faster you go, the more concentrated this effect becomes. Now, imagine you somehow hit the ultimate speed limit, light speed itself. At that moment, the situation becomes almost incomprehensible. From the perspective of an object moving at light speed, which, again, is purely theoretical because objects with mass cannot achieve it, the equations of relativity imply that time stops entirely. Time for the traveler effectively freezes. But not only that, space ahead becomes a kind of barrier. Photons emitted by distant stars can no longer overtake you in the normal way because you are moving at the same speed they are traveling. The universe ahead cannot catch up to your eyes. What does this look like visually? Essentially, you would see nothing ahead. The stars, galaxies, and all luminous objects in front of you would vanish from view, not because they cease to exist, but because their light cannot reach you at the normal pace. You would be running alongside the photons themselves, so they would never enter your eyes in the conventional sense. The forward universe collapses into invisibility. Behind you, light would still be approaching, but the forward field, a space you're attempting to traverse at the ultimate speed, becomes a kind of lightless void. It's as though you are pressing against an invisible wall, the light wall, beyond which the normal propagation of light cannot occur. The light wall is more than a visual oddity. It is a profound physical manifestation of relativity's ultimate limit. It illustrates why no material object can reach light speed. At that boundary, the universe itself refuses to transmit information to you in the normal way. Photons, which carry information about the positions, shapes, and motions of everything in the cosmos, can no longer do their job ahead of you. The concept of a forward-facing view breaks down entirely. At light speed, your forward vision ceases to exist, time halts, and space in the direction of travel collapses into a limit that cannot be crossed. The light wall also underscores the connection between speed, energy, and perception. As you approach light speed, the energy of incoming photons ahead increases dramatically due to blue shifting. Even before reaching the theoretical limit, this concentrated radiation would become dangerous or fatal. By the time you hypothetically reach light speed, the universe ahead isn't just invisible, it's a wall of infinite energy that no known material object can survive. It's the universe's ultimate speed limit made tangible, an insurmountable barrier both physically and visually. Philosophically, the light wall illustrates the boundary between possibility and impossibility in the universe. It's not an arbitrary speed limit set by human engineering or imagination. It is a natural consequence of the way space, time, and light are interconnected. Beyond it, conventional notions of motion, observation, and causality begin to unravel. The wall is a warning embedded in the fabric of reality itself. Some velocities are forbidden not by technology, but by the universe's deep architecture. It's also a deeply humbling reminder of our own limitations. No matter how advanced our spacecraft become, no matter how powerful our engines, the light wall ensures that certain things remain forever beyond our grasp. The stars ahead, no matter how bright or close, are unreachable in the instantaneous sense. The light that defines the structure and information of the universe cannot be caught up to. We can approach, we can get extremely close, but the ultimate boundary, the speed of light, remains untouchable, and along it, the universe becomes unknowable in a very literal sense. Finally, the light wall provides a striking visualization of why all the other relativistic effects we've discussed, time dilation, length contraction, Doppler shifting, and the warping of vision, exist. They are all preambles to this final limit, consequences of the cosmic rule that light speed is a fixed, universal boundary. The universe stretches, bends, and compresses space and time to enforce that limit, and the light wall is the point where these adjustments reach their extreme. A forward void beyond which no traveler can see, no photon can approach, and no mass can penetrate. As we push further into the extreme consequences of approaching light speed, we encounter a realm where the familiar order of events, the chain of cause and effect, begins to unravel. This is what physicists refer to when discussing causality breakdown. In everyday life, causality feels absolute. You flip a light switch, and the bulb illuminates. You press the accelerator, and the car moves forward. There's a clear, linear sequence. Cause precedes effect, and the past is fixed, while the future is yet to come. But near the cosmic speed limit, and especially in any hypothetical scenario involving faster-than-light travel, this straightforward logic begins to fail. At the heart of this lies a consequence of special relativity. Simultaneity is relative. Two events that appear to happen at the same time to one observer may occur in different sequences to another observer moving at a high velocity. For instance, imagine two lightning strikes hitting a train simultaneously according to someone standing on the ground. To a passenger speeding past on the train, the strikes may not appear simultaneous at all. One could occur before the other. At everyday speeds, this difference is imperceptibly tiny, but as you approach light speed, these discrepancies grow enormous. Events that seem causally connected in one frame of reference may appear out of order in another. Now, consider what happens if faster-than-light travel were possible, even in theory. If you could move faster than light, you could traverse space in such a way that, from some observers' perspectives, you arrive before you left. This is not a minor wrinkle, it's a fundamental paradox. Imagine sending a message to a distant star faster than light. In one reference frame, the message leaves Earth and arrives at the star moments later. In another frame, moving at high velocity relative to Earth, the message could arrive before it was sent. Suddenly, the neat, linear progression of time, past, present, future, breaks down. You could, in theory, influence events that have already happened according to another observer. This leads to the infamous grandfather paradox, often used to illustrate the logical contradictions inherent in faster-than-light travel or time travel. If you could somehow go back and prevent your grandfather from meeting your grandmother, you would erase your own existence. But if you never existed, then how could you have traveled back to prevent their meeting? Faster-than-light travel opens the door to such paradoxes because it allows for scenarios where cause and effect are no longer guaranteed to align in a universal sequence. The universe, as we understand it, simply cannot tolerate these contradictions. Even more subtly, causality breakdown is tied to the very flow of information. The speed of light is not just a limit on physical motion, it's the ultimate speed limit for the transmission of information. If you could exceed it, you could send signals into the past, creating loops where the same piece of information could theoretically exist before it was ever created. This is why physicists emphasize that light speed is inviolable. It preserves the logical consistency of cause and effect across the universe. Without that limit, the structure of reality itself would fracture. To make this more concrete, imagine two observers in relative motion, Alice on Earth and Bob traveling near light speed. If Bob were somehow able to surpass light speed, he could send information back to Alice in such a way that she receives it before he departed. She might act on this information, inadvertently changing the conditions that caused Bob's journey in the first place. These are not just thought experiments, they are logical consequences of relativity when combined with faster-than-light assumptions. Even though physically impossible, they highlight why relativity enforces a cosmic speed limit. The universe is protecting its own logical consistency. The breakdown of causality also has implications for our understanding of time itself. At sublight speeds, time is relative but predictable. Everyone agrees on the sequence of cause and effect when considering local events. Approaching light speed introduces extreme time dilation, stretching and warping experiences across different frames. But surpassing light speed would erase that predictability entirely. The very notion of before and after would lose meaning in certain frames of reference, making the universe a place where chronological order is fluid, and paradoxes could proliferate uncontrollably. Even if faster-than-light travel were hypothetically possible for particles like tachyons, which are purely theoretical and always move faster than light, the consequences would be profound. Interactions between tachyons and normal matter could result in causality violations, with events triggered by particles before they existed in conventional time. This isn't just academic. It demonstrates that the speed of light limit isn't arbitrary. It is woven into the fabric of causality, the very principle that allows the universe to be logically coherent. In essence, the laws of cause and effect are the skeleton of reality, holding together everything from the motion of planets to the life cycles of stars and the progression of human events. Special relativity shows that even at sublight speeds, time and space are flexible, but still coherent. Push beyond that boundary, and the skeleton begins to collapse. The universe becomes a place where effects can precede causes, where logical contradictions emerge, and where the narrative structure of reality itself unravels. That's why faster-than-light travel isn't just practically impossible, it's philosophically and logically forbidden. Causality breakdown also frames the other relativistic effects we've discussed. Time dilation, length contraction, Doppler shifting of light, and the light wall are all mechanisms that prevent violations of cause and effect. They enforce a cosmic order. No observer can outrun light, no traveler can witness the future before the present, and no paradoxes arise in the physical laws. In this sense, relativity is not merely a set of mathematical formulas. It is the universe's way of protecting its own coherence. As we delve further into the consequences of approaching light speed, the issue of energy becomes unavoidable. It is one of the most fundamental reasons why no object with mass can ever reach the speed of light. While the mathematics of relativity paints an elegant picture of time dilation and length contraction, it also delivers a harsh reality. Accelerating an object to light speed would require an infinite amount of energy. And in our universe, Infinity isn't just inconvenient, it is physically impossible. To understand this, we return to the concept of relativistic mass, which we explored earlier. As an object accelerates and its velocity approaches the speed of light, its effective mass increases. From the perspective of an outside observer, the object becomes harder and harder to push. You might think of it like trying to roll a boulder uphill. The faster you go, the steeper the hill becomes. Unlike a hill in the physical world, however, this relativistic hill gets infinitely steep as you approach light speed. Every additional fraction of velocity requires ever more energy. Mathematically, the total energy of a moving object is given by the equation E=gamma mc squared, where m is the rest mass, c is the speed of light, and gamma, the Lorentz factor, is equal to 1/sqrt, 1 minus v squared divided by c squared. Here's the key point: as v approaches c, the denominator of that fraction approaches 0, making gamma grow without bound. In other words, your energy requirement escalates toward infinity. You can double your energy, triple it, 100-fold it, but no finite amount will ever get you all the way to light speed. The closer you try to get, the more energy the universe demands, and the more impossible it becomes to satisfy that demand. To make this tangible, imagine trying to accelerate a spaceship with a mass of 1,000 kilograms to 99% of light speed. The amount of energy required is enormous, millions of times the energy released by all the nuclear weapons on Earth combined. If you attempt 99.999% of light speed, the energy required grows to inconceivable levels, approaching the output of entire stars over years. And at 100% light speed, the energy needed becomes literally infinite. In practical terms, infinity is not just a number. It is a concept that cannot exist as usable energy in the physical world. Our engines, fuel, and even the total energy content of the known universe are finite, which makes reaching light speed fundamentally impossible. This energy problem is closely tied to the mass increase we discussed earlier. As your relativistic mass grows, every increment of speed demands exponentially more energy. It's a feedback loop. Acceleration increases mass, increased mass requires more energy, and more energy increases the difficulty of further acceleration. Eventually, as you approach the speed of light, the energy curve becomes vertical. No finite amount of energy can push you past the cosmic barrier. Even if we imagine near-future or futuristic propulsion technologies, fusion drives, antimatter engines, or hypothetical warp drives, the energy problem remains. No matter how efficient your engine, no matter how advanced your technology, you are still bound by the relativistic laws of energy and mass. Infinite energy simply does not exist in the universe. And because energy is required to accelerate mass, this limit is absolute. It is not a technological challenge, it is a physical law. We can also see this effect in particle accelerators. High-energy protons in the Large Hadron Collider are accelerated to over 99.999999% of light speed. To achieve each increment of speed closer to the speed of light requires vastly more energy than the previous increment. Despite the LHC's enormous power, the protons never reach light speed. Their energy skyrockets toward theoretical infinity, making further acceleration physically impossible. This is not a failure of engineering. It is relativity in action, enforcing the ultimate cosmic speed limit. The energy problem also explains why photons, the particles of light, can move at light speed, while massive objects cannot. Photons have zero rest mass. Because the energy required to accelerate mass depends on having rest mass, photons can move at light speed without requiring infinite energy. They are fundamentally different from particles like electrons, protons, or spaceships. The universe allows light to reach its ultimate velocity because it carries no rest mass, and thus the energy barrier that traps massive objects does not apply. In broader terms, the energy problem illustrates the profound link between speed, mass, and energy in the universe. It is a concrete manifestation of relativity's laws. As you move faster, your world changes. Time slows, distances shrink, your vision warps. But the universe also protects itself, enforcing boundaries that cannot be crossed. Energy is the currency of motion, and at light speed, the cost is infinite. The law that forbids faster-than-light travel is written into the cosmos itself. This principle has deep philosophical implications as well. It reminds us that the universe is not infinitely malleable. No matter how ambitious our technological dreams, there are natural limits to what is physically achievable. It is not a matter of willpower or ingenuity. It is a property of reality. The energy wall at light speed serves as a guardrail, keeping the cosmic order intact and preventing paradoxes that would arise from faster-than-light travel. In essence, the energy problem is the ultimate expression of why light speed is unattainable for objects with mass. It ties together mass increase, time dilation, length contraction, and causality. It is the reason why our hypothetical astronaut can experience a year of near-light speed travel while decades pass on Earth, but cannot actually cross the barrier into the realm of true light speed existence. The laws of physics enforce consistency, coherence, and causality through this seemingly simple but profoundly restrictive principle. Infinite energy is impossible, and therefore so is light speed travel for anything that has mass. As we venture into the speculative fringes of physics, the concept of tachyons emerges, a class of hypothetical particles that exist purely in theory and would, if they exist, always move faster than light. Tachyons are fascinating because they occupy a unique niche in the framework of relativity. Unlike ordinary particles, which are constrained by the speed of light as an upper limit, tachyons are, by definition, forbidden from slowing down below light speed. They inhabit a world that is effectively the mirror image of what massive objects experience in relativity. The idea of tachyons originates from the mathematical solutions to the equations of special relativity. When physicists solve the energy-momentum relationship for particles, there exists a set of solutions that imply negative mass squared, which would correspond to particles always traveling faster than light. These solutions are not forbidden by the mathematics itself. They simply lead to consequences that are extremely strange and counterintuitive. For example, tachyons, if they existed, could appear to travel backward in time from certain reference frames, seemingly violating causality. That's one of the reasons why they remain hypothetical. Their existence would challenge fundamental principles of cause and effect, and no experimental evidence has ever confirmed their presence. One of the key theoretical properties of tachyons is that they cannot slow down to or below the speed of light. If they did, their energy would become imaginary, a nonsensical quantity in physical terms. Conversely, as a tachyon loses energy, its speed actually increases. This is the exact opposite behavior of ordinary matter, where adding energy increases velocity, but you can never reach light speed. Tachyons flip that rule entirely, making them extraordinarily exotic from both a mathematical and conceptual standpoint. Because of these extreme properties, tachyons have inspired a lot of speculation in science fiction and theoretical physics. Some proposals have imagined using tachyons to send signals faster than light, which could, in principle, allow communication across vast interstellar distances almost instantaneously. Others speculate about tachyons as tools for probing the boundaries of causality or as mechanisms in hypothetical models of time travel. But all of this remains entirely speculative. No experimental detection of tachyons has ever occurred, and their existence is not predicted by any standard model of particle physics. From a relativistic perspective, tachyons serve as a fascinating thought experiment because they highlight the symmetry of the speed of light barrier. Just as massive particles cannot reach or exceed light speed, tachyons cannot slow down below it. Both types of particles illustrate the universality of the cosmic speed limit, but from opposite directions. The speed of light becomes a dividing line in spacetime. Ordinary matter is trapped below it, photons exist exactly at it, and tachyons, if they exist, would be trapped above it. It's also worth noting that tachyons are a reminder of the delicate balance in our physical theories. Their mathematical possibility shows that relativity allows a wider spectrum of solutions than are realized in nature. But the universe has its own checks and balances. So far, it appears that tachyons do not manifest in our observable reality. Their purely theoretical existence emphasizes that the laws of physics are consistent and self-protecting, preventing causal paradoxes in the real world while still permitting the imagination to explore extreme possibilities. In summary, tachyons are hypothetical, faster-than-light particles that arise from mathematical solutions to relativity's equations. They would always travel faster than light, cannot slow down, and theoretically could violate causality. Yet despite their intriguing properties, no evidence supports their existence, and they remain firmly in the realm of theoretical physics. Their story demonstrates both the elegance and the limits of our understanding, showing what the universe allows mathematically, even if it does not permit physically. To fully grasp the profound effects of near-light speed travel, it helps to focus on the comparison between everyday time as experienced on Earth and the subjective time experienced by a traveler moving close to light speed. This is where the abstract mathematics of relativity become deeply personal, affecting the very passage of life itself. In relativity, time is not universal. There is no single, absolute clock ticking across the cosmos. Instead, time is relative to the motion of observers. The faster you move, the more your personal time slows down compared to someone who remains at rest. Consider our familiar scenario of a spaceship traveling at 99% of the speed of light toward a star 10 light-years away. On Earth, observers would calculate that the journey takes just over 10 years because the ship is moving very close to the speed of light but not quite there. That's everyday time measured by clocks on Earth. Meanwhile, inside the spacecraft, the astronaut's experience is vastly different. Thanks to time dilation, the Lorentz factor at 99% of light speed is about 7. This means that for every 7 years that pass on Earth, the astronaut experiences only 1 year of subjective time. 1 Earth year is stretched across the astronaut's 7-year Earth time span, compressing the journey to a fraction of its apparent duration. The difference becomes even more dramatic at 99.9% of the speed of light, where the Lorentz factor jumps to about 22. 1 year aboard the spacecraft corresponds to 22 years passing back on Earth. Imagine returning from what feels like a relatively short expedition, only to discover that decades have passed on your home planet. Friends and family have aged, societies have evolved, and entire cultural and technological landscapes may have shifted, while the traveler has experienced a comparatively tiny sliver of time. For a more extreme illustration, consider the thought experiment often cited in theoretical physics, traveling at 99.999999% of the speed of light. Here, the Lorentz factor can reach thousands. A single year aboard the spacecraft could correspond to millennia passing on Earth. From the astronaut's perspective, she has taken a short trip. From Earth's perspective, an entire civilization may rise and fall during her absence. The gulf between subjective and external time underscores the relative, non-absolute nature of temporal experience in the universe. This relativity of time also affects aging, biological processes, and even psychological perception. The astronaut's heartbeat, metabolism, and cellular function continue normally in her frame of reference. Her personal sense of time is uninterrupted, as though nothing extraordinary has occurred. Meanwhile, clocks on Earth tick away rapidly in comparison, reflecting decades or centuries. Relativity allows these two experiences of time to coexist without contradiction, even though they are radically different. Each frame of reference, Earth and spacecraft, is internally consistent, yet the discrepancy highlights the profound way motion shapes reality. The everyday implications of this relativity are profound. Time is often considered a fixed, universal rhythm, but near-light speed travel reveals that the passage of time is contingent on motion. For instance, an astronaut might leave Earth in the year 2100, spend a decade traveling at near-light speed, and return to find that the Earth year is 2150 or later. What felt like a 10-year journey to the traveler has stretched into half a century of Earth time. Relativity ensures that both timelines, the travelers and the Earthbound observers, are equally real, even though they diverge dramatically. This comparison also helps illustrate why interstellar travel, while theoretically feasible in terms of human lifespans, presents practical and philosophical challenges. Even if astronauts could traverse vast distances without aging significantly, they would experience a temporal disconnect with everyone left behind. Societies, cultures, and personal relationships would advance while the traveler perceives only a small fraction of that time. The relativity of time creates a profound tension between human desire for exploration and the reality of universal laws. In more everyday terms, even small velocities create measurable but subtle differences. Astronauts aboard the International Space Station orbit Earth at approximately 27,000 kilometers per hour. Their clocks run slightly slower than those on Earth, resulting in a time discrepancy of a few milliseconds over the course of a 6-month mission. While imperceptible in human terms, this effect is exactly the same principle as the dramatic differences experienced at near-light speeds, only magnified. Relativity operates consistently across all scales, from the millisecond differences of low Earth orbit to millennia of hypothetical interstellar journeys. Ultimately, The comparison between everyday time and traveler time forces us to re-evaluate our intuitions. Time is not a single universal current, but a personal experience shaped by motion through space. The faster you move relative to others, the slower your clock runs compared to theirs. For near-light speed travelers, this means that years can stretch into decades or centuries elsewhere, and what feels like a brief journey can coincide with the passage of entire human generations back on Earth. Relativity transforms time from an absolute measure into a flexible, relative dimension, one that depends fundamentally on motion and perspective. From the perspective of someone watching a near-light speed traveler from Earth, the universe behaves in ways that are as mind-bending as they are counterintuitive. While the traveler experiences time slowing down in their own frame of reference, an outside observer sees the opposite effect manifested visually. The traveler appears to move slower and slower, almost as if they are frozen in time. This phenomenon is a direct consequence of time dilation, one of the core predictions of special relativity, and it has profound implications for how we perceive motion at relativistic speeds. Imagine a spacecraft accelerating toward 99% of the speed of light. From the astronaut's own perspective, everything inside the vessel operates normally. Clocks tick steadily, conversations occur at familiar rhythms, and biological processes proceed without disruption. However, someone standing on Earth observing the ship through a telescope or other instruments perceives a very different reality. Because of the relativistic effects on time, the astronaut's movements appear dramatically slowed. If the traveler raises their hand, Earth observers would see the hand move painstakingly slowly, as though time itself has become viscous for the person aboard the ship. The effect becomes more extreme as the traveler's speed approaches light speed. At 99.9% of the speed of light, the time dilation factor is roughly 22. This means that for every year experienced by the traveler, 22 years pass for those on Earth. To the Earth observer, the astronaut is moving at roughly 1/22nd the normal speed, a tiny fraction of real-time motion. Gestures, speech, even the rotation of the spacecraft would appear sluggish, stretched out across the timeline of Earth-based observers. The traveler seems trapped in a slow-motion bubble, their passage through time almost frozen from an outside perspective. This perception is not just a theoretical curiosity, it has measurable consequences in particle physics. For example, unstable particles moving at relativistic speeds appear to decay more slowly from the perspective of stationary detectors. High-energy muons created in the upper atmosphere by cosmic rays reach Earth's surface because their internal clocks slow dramatically at near-light speeds, consistent with what stationary observers would predict. Just as scientists see these particles survive longer than expected, an Earthbound observer would see a high-speed traveler moving as if time itself were stretched. From a visual standpoint, the phenomenon is astonishing. Suppose an astronaut is on a journey to a nearby star system and is broadcasting a video feed back to Earth in real time. Because of time dilation, the video would appear extremely slowed down. Even subtle motions, like blinking or adjusting equipment, would be stretched over minutes, hours, or years depending on the astronaut's velocity. If the ship accelerates closer to light speed, the effect intensifies, approaching an almost frozen tableau of the traveler's existence. Interestingly, the slowing of perceived motion is compounded by relativistic aberration and the Doppler effect. Light emitted from the moving ship is redshifted for the observer behind it, stretching not just the spatial movement but also the observed frequencies of radiation and signals. This means that the traveler's voice, light signals, or even the color of the ship may appear altered, further reinforcing the illusion of extreme sluggishness. Observers would witness a combination of motion slowdown, color shift, and visual distortion, a composite effect of multiple relativistic phenomena all working simultaneously. This perception highlights the relative nature of time in an even more dramatic way. While the traveler feels only brief periods passing, Earth observers see those same intervals stretched to years or decades. Both viewpoints are correct, consistent, and governed by the laws of physics. Yet they are radically different, illustrating that motion through space does not just affect speed, it affects the fundamental experience of time itself. The implications for communication are profound as well. If someone traveling near light speed tried to transmit a live message to Earth, the transmission would be received incredibly slowly due to both time dilation and the speed of light delay. From Earth's perspective, the traveler seems almost suspended in time, their activities unfolding at a glacial pace. Messages intended to provide immediate information become hopelessly delayed, demonstrating how relativity reshapes even our concept of interaction and observation. Philosophically, the outside observer effect is a reminder of the relativity of reality. There is no universal now that spans the cosmos. Each observer has their own proper time. The traveler's present is not the same as the earthbound present. What seems immediate and ordinary to the astronaut may appear frozen or distorted to anyone else. The universe accommodates all observers simultaneously, but it does so by bending both space and time in ways that defy common intuition. This effect also reinforces the importance of perspective in physics. It underscores why Einstein's insights were revolutionary. The laws of physics are the same for all observers, but the perception of time and motion depends fundamentally on relative velocity. Earth-based observers are not wrong to see a slowed traveler. They are simply seeing time unfold according to their own frame of reference, just as the traveler experiences their own journey according to theirs. Both observations are valid, and both are essential for a consistent understanding of the relativistic universe. As we move deeper into the implications of near-light speed travel, the question of communication becomes not just a technical challenge but a fundamental physical limitation. The same relativistic principles that warp time, space, and perception also conspire to make sending or receiving messages at or near the speed of light increasingly problematic, to the point of becoming essentially meaningless in practical terms. Understanding this requires an exploration of the intertwined effects of time dilation, relativistic Doppler shifts, and the finite speed of light itself. Consider an astronaut traveling at 99.9% of the speed of light toward a distant star. Suppose she wants to send a signal back to Earth, a simple text message, for instance. Even though the signal itself moves at light speed, the distance between her and Earth continues to change almost as fast as the light can traverse it. In relativity, the speed of information is limited by c, the speed of light, and no signal can outrun that limit. At such extreme velocities, the relative motion compresses or stretches the perceived timing of signals dramatically. To Earth observers, the messages from the astronaut would arrive at irregular intervals, first delayed and then increasingly stretched over time, making them difficult to interpret in any conventional sense. The relativistic Doppler effect further complicates communication. Signals sent forward toward the direction of travel are blue-shifted, meaning their frequency increases. At low relativistic speeds, this manifests as a slight increase in frequency, maybe a higher-pitched radio signal. At speeds approaching light speed, however, the blue shift becomes extreme. For example, radio signals could shift into the ultraviolet, X-ray, or even gamma-ray range, rendering ordinary receivers useless. Conversely, signals sent backward, away from the direction of motion, experience extreme redshift, stretching their wavelengths so dramatically that they may no longer carry usable information. The message might still be traveling through space, but it is arriving in a form that cannot be interpreted without specialized, perhaps impossible, instrumentation. Time dilation compounds the problem. The astronaut's proper time, the time she experiences on her own clock, is dramatically shorter than the elapsed time on Earth. A signal sent every minute according to her watch would be received on Earth years apart, depending on her velocity. Earth-based receivers would perceive the astronaut's communications as painfully slow, potentially spanning decades for what felt like minutes or hours to her. This mismatch makes real-time or even near-real-time communication infeasible. The concept of instant messaging loses all meaning when relativistic effects are in play. Another profound challenge arises from the finite speed of light itself. Even if relativistic distortions were somehow corrected, the sheer distances involved in interstellar travel mean that signals take years, decades, or even centuries to arrive. If an astronaut is traveling near light speed toward a star system 10 light-years away, any message sent to Earth from the midpoint of the journey would still take nearly 10 years to arrive. By the time the signal reaches Earth, the conditions in the astronaut's vicinity could have changed drastically, rendering the information obsolete. The faster the traveler moves, the more out-of-sync Earth and ship experiences become, amplifying the irrelevance of any transmitted messages. This breakdown of communication has practical consequences for both exploration and human connection. Families on Earth would struggle to communicate meaningfully with near-light speed travelers. Mission Control would find it almost impossible to coordinate or monitor spacecraft activities in real time. Even for scientific purposes, the data arriving from relativistic missions would be staggered and skewed, requiring complex calculations to reconstruct events as they occurred in the traveler's frame. Communication is not merely delayed, it is distorted, scrambled by the interplay of motion, time dilation, and frequency shifts. There is also a philosophical dimension. Communication is the bridge that links experiences across space and time. In the relativistic regime, that bridge begins to fracture. The faster you move, the more your personal timeline diverges from the timelines of everyone else. Your attempts to share information become less about connecting and more about projecting a snapshot from a radically different temporal frame. At near-light speed, your messages may arrive decades, centuries, or millennia later, when the original context has vanished. Meaning itself, shared understanding, synchronization of events, real-time interaction, becomes elusive. Even hypothetically, were we to envision advanced methods such as quantum entanglement or exotic tachyonic communication, fundamental limitations still persist. Special relativity forbids faster-than-light signaling, precisely because allowing it would violate causality. Any attempt to circumvent the light speed limit would risk sending information backward in time, creating paradoxes akin to the grandfather paradox. In other words, meaningful communication at or beyond light speed is not merely technologically challenging, it is forbidden by the laws of physics themselves. In short, communication breaks down at relativistic speeds due to a combination of time dilation, Doppler shifting, and the finite speed of light. Messages sent from the traveler to Earth become delayed, distorted, and stretched across incomprehensible time intervals. Signals may shift out of detectable wavelengths, and even if received, they may arrive long after the context has changed or disappeared. From both a practical and a physical standpoint, sending or receiving meaningful messages at near-light speed travel is effectively impossible. The universe enforces this limitation, ensuring that while travel near light speed might be theoretically achievable, instantaneous or synchronized communication across such journeys remains a dream forever beyond our reach. Traveling at speeds approaching that of light is not just a theoretical exercise in physics, it is a profound challenge for biology. The human body, evolved for life on Earth under gentle gravity and moderate radiation levels, would face stresses at relativistic velocities that are utterly beyond anything we experience in daily life. These effects are not just uncomfortable, they border on lethal, raising questions about whether any known life form could survive near-light speed travel without extraordinary protection. First, consider the forces involved in acceleration. To reach relativistic speeds, a spacecraft must accelerate gradually to avoid crushing the occupants, because the human body can withstand only so much g-force before organs, bones, and blood flow fail. Even with carefully engineered acceleration protocols, the stresses on the skeletal and cardiovascular systems would be extreme. Any miscalculation could result in immediate trauma. In a conventional rocket, the g-forces might already limit astronauts to a few times Earth gravity for extended periods. To accelerate toward a significant fraction of light speed in a reasonable time frame, the forces required are astronomical, necessitating either decades of near-continuous gentle acceleration or some hypothetical method of propulsion that produces high speeds without subjecting passengers to lethal inertial forces. Cosmic radiation presents another profound challenge. Even at relatively low speeds, astronauts are exposed to charged particles from the Sun and cosmic rays from deep space. At near-light speed, these effects are amplified dramatically. The energy of incoming particles relative to the spacecraft increases due to relativistic Doppler effects, turning harmless cosmic rays into deadly beams of high-energy radiation. The blue shifting of incoming photons would transform the entire electromagnetic spectrum ahead of the ship into hazardous ultraviolet and X-ray radiation, as we discussed in the Vision at Light Speed segment. The human body has almost no natural defense against such a barrage. Without extremely advanced shielding, likely requiring materials far beyond what we currently possess, the radiation exposure would be fatal in short order. Temperature management and energy deposition are also critical concerns. At relativistic speeds, the kinetic energy of even tiny particles encountered in the interstellar medium becomes extreme. A single hydrogen atom colliding with a spacecraft moving at 99.99% of light speed carries energy equivalent to a macroscopic projectile traveling at conventional ballistic speeds. Impact with interstellar gas and dust would produce intense localized heating, potentially burning through protective shielding or vaporizing exposed materials. Any human inside the ship would be at risk of both direct radiation and indirect thermal effects, requiring engineering solutions that are currently far beyond our technological reach. Beyond these external threats, the internal physiology of the human body would be affected by time dilation in subtle ways. Biological processes, metabolism, cell division, hormone cycles, and neural signaling would continue normally in the traveler's frame of reference, but the relative slowness of time for external observers would create an almost alien disconnect. From the perspective of Earth, the traveler's heartbeats, movements, and aging appear extraordinarily slow. While not harmful in itself, this creates psychological and operational challenges if synchronization with Earth-based systems or communication is required. Moreover, the extreme speeds would amplify micro-accidents into potentially catastrophic events. Tiny misalignments in shielding or navigation could result in collisions with particles or radiation fluxes that are otherwise negligible at normal velocities. The energy densities involved are so high that what seems like a small flaw in shielding could have lethal consequences. This is not speculative exaggeration. Calculations of relativistic particle impacts show that interstellar travel at near-light speeds is a serious hazard for both human biology and spacecraft integrity. Even more speculative are the potential effects on the nervous system and perception. Humans evolved under constant gravitational and sensory conditions. Traveling near light speed introduces extraordinary visual distortions, extreme Doppler shifts in radiation, and forces that may interfere with vestibular systems. The astronaut would experience a reality that is simultaneously compressed and stretched, the forward universe compressed into a bright, potentially blinding cone of radiation, the rearward universe vanishing or redshifted out of perception. The brain's neural networks may struggle to process these inputs, and sensory overload could produce disorientation or incapacitation. Finally, there is the ultimate biological consequence of theoretical light-speed travel, the effective freezing of time from the traveler's perspective. If it were somehow possible to reach exactly light speed, the traveler's subjective experience of time ceases. While we cannot know exactly how biology would respond to a frozen time state, since no known mass can reach light speed, it raises fundamental questions about cellular metabolism, energy utilization, and consciousness. If time stops, do biochemical reactions cease as well? These are questions for which we have no empirical answers, but they highlight the profound gulf between human-scale experience and the extreme conditions of relativistic travel. In sum, traveling at near-light speed imposes a cascade of lethal challenges: extreme acceleration forces, deadly cosmic and high-energy radiation, particle collisions, thermal hazards, and sensory distortions. Even with perfect engineering and shielding, the biological toll would be extraordinary. The human body is a delicate, evolved system finely tuned to earthly conditions, and the relativistic cosmos is fundamentally hostile to life as we know it. Survival would require not only exceptional technological innovation but also profound adaptations or protections beyond our current understanding. If a human, or any object with mass, could somehow ride alongside a beam of light, the consequences for the perception of time would be utterly alien. According to Einstein's special relativity, as one approaches the speed of light, time dilation becomes extreme. For a massless particle like a photon, which inherently travels at light speed, time does not progress at all. From the perspective of that photon, or a hypothetical traveler somehow moving at light speed, there is no passage of time. In this frame, billions of years of cosmic history could unfold in the universe while the traveler experiences the journey as effectively instantaneous. This phenomenon is a direct consequence of the relativistic time dilation formula, T equals T\gamma, where T is the elapsed time for a stationary observer and T is the elapsed time for the moving observer. The Lorentz factor \gamma equals 1\sqrt, 1 minus v squared divided by c squared, grows without bound as velocity v approaches the speed of light c. As v nears c, \gamma approaches infinity, and thus t approaches zero. No matter how long an observer on Earth waits, millions, billions, or even trillions of years, the traveler experiences that interval as essentially non-existent. For a true photon, which exists precisely at light speed, the factor becomes infinite, making the experience of time literally non-existent from its frame of reference. This has astonishing implications for perspective and experience. From the earthbound observer's viewpoint, galaxies evolve, stars are born and die, and civilizations rise and fall over eons. For a photon, or a hypothetical light-speed traveler, this entire cosmic history unfolds in a timeless instant. The journey from one side of the universe to the other, which would take billions of years for observers in stationary frames, is instantaneous in the traveler's frame. The photon exists at all points along its trajectory simultaneously. It does not age, does not change, and experiences no passage from emission to absorption. This raises profound philosophical questions about time itself. Our intuitive understanding of cause and effect, of past, present, and future, is built on the steady progression of time. But at light speed, these categories dissolve. Events along the photon's path exist in a kind of superposition from its perspective. The Big Bang, the formation of galaxies, and the eventual collapse of stars are all equally present in the photon's experience. There is no before or after. Time is an external construct that has no meaning at this extreme of velocity. If we entertain the notion of a human somehow achieving this impossible feat, the consequences are staggering. A traveler accelerating asymptotically toward light speed would see time outside their frame rushing forward at incomprehensible rates. Civilizations would rise and fall, stars would be born and die, galaxies would collide, and the universe could evolve from a young, vibrant cosmos to a dark, cold expanse, all while the traveler's own subjective experience registers merely minutes, seconds, or nothing at all. The traveler would witness effectively the entire lifespan of the cosmos compressed into a nearly instantaneous journey, with no awareness of its duration. This also underscores why light-speed travel is fundamentally different from near-light speed travel. Near light speed, time dilation is extreme but finite. Travelers can experience months or years while decades or centuries pass elsewhere. But at the speed of light itself, the dilation factor becomes infinite, reducing the traveler's experience of time to zero. The boundary between near-light speed and light speed is thus a radical conceptual threshold. Approaching it, you stretch your own experience while compressing the universe. Crossing it, even hypothetically, annihilates subjective time entirely. Another striking implication involves distance perception. Alongside extreme time dilation, length contraction occurs in the direction of travel. For a traveler moving at near-light speed, distances to stars and galaxies shrink dramatically. If one could truly reach light speed, the distance along the direction of motion contracts to zero. In other words, for a light-speed traveler, the entire universe collapses along the line of motion. Space and time in that direction vanish, and the journey from one end of the cosmos to another is instantaneous. The combination of time dilation and length contraction illustrates the extreme way relativity warps reality, merging space and time into a continuum that becomes unrecognizable at light speed. It's important to stress that this is purely theoretical. Objects with mass cannot reach light speed, and any hypothetical human could never experience true timeless travel. Nevertheless, imagining this scenario illuminates the profound consequences of relativity for our understanding of time, space, and the universe. It allows us to see that the cosmic scales of billions of years, which seem utterly vast and incomprehensible to humans, could appear instantaneous from the perspective of a light-speed trajectory. Time is no longer a flowing river but a malleable dimension shaped by motion, velocity, and the fundamental structure of space-time. This thought experiment also reshapes how we consider cosmology. For Earthbound observers, the universe has a measurable age, currently about 13.8 billion years. From a photon's perspective, however, this entire span is traversed in no time at all. This contrast highlights the relativity of time not as a theoretical curiosity but as an intrinsic property of reality. The universe ages differently for every observer depending on their motion. The same cosmic history that seems gradual and sequential to us is instantaneous for a light-speed traveler, underscoring the profound way relativity unifies time and space into a single continuum. Traveling near the speed of light transforms the universe from an almost incomprehensibly vast expanse into a more approachable, though still extraordinary, realm. For someone moving at relativistic speeds, distant galaxies that would otherwise take millions or even billions of years to reach using conventional propulsion suddenly become accessible within the traveler's lifetime. This is a direct consequence of the interplay between time dilation and length contraction, two fundamental predictions of Einstein's special relativity. From the traveler's perspective, the cosmos shrinks along the direction of motion, while their subjective experience of time slows relative to stationary observers. Consider a spacecraft accelerating to 99.999% of the speed of light. To observers on Earth, traveling even to the nearest galaxy, Andromeda, over 2.5 million light-years away, would take more than 2.5 million years at sublight speeds. Such a journey is, of course, utterly beyond human timescales. However, for the relativistic traveler, time dilation compresses their subjective travel duration. Using the Lorentz factor, we see that the traveler's experience could be reduced to mere decades or even years. From the traveler's frame, the distance to Andromeda itself is also contracted due to length contraction, making the journey feel even shorter. In effect, galaxies that appear staggeringly remote from Earth become accessible in a human lifetime. This creates a stark divergence between the traveler's experience and the passage of time back home. While the astronaut may complete the journey to Andromeda in what feels like 10 or 20 years, thousands or millions of years may have elapsed on Earth. Entire civilizations could rise and fall, stars could burn out, and the cosmic environment could evolve dramatically before the traveler returns, or even sends messages back. This disparity highlights one of the strangest consequences of near-light speed travel. The traveler ages very little while the universe outside continues its vast, relentless progression. The idea of cosmic horizons also emphasizes the relativity of distance and time in motion. The traveler experiences contracted distances along their line of travel. For example, a galaxy that is 2 million light-years away in the Earth frame might appear only a few hundred light-years distant to the traveler. The universe effectively compresses along the direction of motion, allowing otherwise impossible journeys to be traversed in practical human lifetimes. While stationary observers perceive the galaxy as far away, the traveler perceives it as reachable, a phenomenon that fundamentally alters the notion of distance when relativistic effects dominate. In addition, the experience of the night sky changes dramatically. As the traveler moves toward distant galaxies, relativistic aberration warps their visual field. Stars and galaxies ahead of the ship cluster into a concentrated region, creating the visual illusion of rushing through a dense tunnel of light. Meanwhile, objects behind fade and redshift out of perception. The combination of contracted distances and distorted visual input produces a sensation of traveling vast intergalactic distances almost effortlessly, though the reality is that these effects are entirely due to the structure of spacetime at high velocities. This raises profound implications for interstellar exploration. If humanity were ever able to achieve speeds approaching that of light, the scope of exploration would expand dramatically. Missions that would have been impossible within human lifetimes suddenly become feasible. Travelers could reach star systems on the other side of the Milky Way or even galaxies beyond, conducting scientific observations or reconnaissance over subjective decades rather than millennia. From the traveler's perspective, vast swaths of the universe are effectively brought within reach, transforming cosmic horizons from impossibly distant to navigable. However, these relativistic advantages come at a cost. While the traveler experiences compressed time, Earth and any other stationary observers experience the full, uncompressed duration. Generational change, societal evolution, and planetary history all continue as usual. An astronaut returning from a relativistic journey could find the home planet dramatically altered, or even unrecognizable, despite having aged only a few decades themselves. Communication with Earth becomes nearly meaningless, as the signals transmitted from the spacecraft are subject to extreme time dilation and Doppler shifting, further emphasizing the disconnection between traveler and homeworld. The concept of cosmic horizons also forces a re-evaluation of what reachable means in a relativistic universe. Traditional notions of distance, time, and travel are intertwined with the observer's frame of reference. Near-light speed travel allows one to exploit relativistic effects to traverse what appears insurmountable in conventional terms. The universe is not shorter in an absolute sense. Rather, it is shorter from the perspective of someone moving at extreme velocity. This is an essential nuance of Einstein's relativity. Space and time are not static backdrops but dynamic entities that depend on motion. In essence, near-light speed travel allows humans, or any travelers, to cross enormous intergalactic distances within their own lifetimes, even though vast stretches of time pass elsewhere in the universe. It demonstrates the staggering flexibility of space-time under relativistic conditions, where subjective experience can diverge dramatically from external reality. The cosmos, normally incomprehensible in scale, becomes navigable in a lifetime, revealing a universe whose horizons are deeply relative, reachable for the traveler but still staggering from the vantage of Earth. One of the most remarkable consequences of the laws of relativity is that light itself can traverse the universe at the ultimate speed limit, while objects with mass cannot. This ability lies at the heart of the distinction between photons, the fundamental particles of light, and any particle that possesses rest mass. The reason photons can travel at light speed is deceptively simple in principle but profound in implication: they have zero rest mass. This property allows them to evade the energy constraints that prevent massive objects from reaching or exceeding the speed of light. To understand why zero rest mass is so crucial, we need to revisit the energy-mass relationship introduced by Einstein's special relativity: E squared equals mc²2 plus pc²2, where E is total energy, m is rest mass, p is momentum, and c is the speed of light. For massive particles, the rest mass term mc²2 dominates when the particle is at rest. To accelerate a massive object toward light speed, you have to provide energy not only to increase its momentum but also to overcome the infinite growth of relativistic mass. That's the energy wall we discussed earlier. For photons, however, m equals 0. This removes the rest mass term entirely, leaving only the momentum-dependent term. A photon's energy is given by E equals pc, meaning it can carry energy while moving at light speed without ever requiring infinite energy. Because they have no rest mass, photons exist in a fundamentally different category of existence compared to ordinary matter. They are never at rest in any reference frame. There is no frame in which a photon is stationary. As a result, they are born traveling at light speed and remain at that velocity eternally, until they are absorbed or scattered. This property allows light to travel unimpeded across the vacuum of space, unaffected by the energy limitations that constrain massive objects. It is the universe's way of ensuring that information, energy, and causality can be transmitted consistently across vast distances. Another key implication of photons' zero rest mass is that they experience no passage of time. As we explored in the universe-age consequences segment, from the perspective of a photon, or hypothetically, an object moving at light speed, time does not progress. A photon emitted from the surface of the Sun reaches Earth in approximately 8 minutes according to an Earthbound observer, but from the photon's perspective, the journey is instantaneous. There is no subjective duration for the photon. It is timeless in its own frame. This is only possible because rest mass is zero. Any object with mass, by contrast, must experience the flow of time and cannot reach this timeless state. The fact that photons travel at light speed also explains why the speed of light is a universal constant. In the equations of special relativity, c is not just the speed of light. It is the maximum speed at which all massless particles and information can propagate. This constancy is embedded in the structure of space-time itself. Photons act as cosmic messengers, carrying energy and information across the universe at the speed limit imposed by the geometry of space-time. Their zero rest mass allows them to fulfill this role without violating the relativistic constraints that govern everything with mass. The zero mass property also underpins phenomena like electromagnetic radiation, radio waves, X-rays, and gamma rays. Each of these manifestations of light, regardless of wavelength or energy level, is composed of photons moving at c. Their energy is proportional to frequency, E equals hf, not to mass. This means high-energy gamma photons can carry immense energy, yet they still travel at light speed because their rest mass is zero. No matter how energetic, they do not encounter the energy barrier that massive particles face when attempting to accelerate towards c. Photons' zero mass also allows them to mediate fundamental forces, such as electromagnetism, instantaneously from the perspective of their frame, while remaining fully consistent with relativistic causality for observers with mass. This is why light and other electromagnetic waves can transmit information over vast interstellar distances without ever exceeding the cosmic speed limit. Photons elegantly navigate the balance between energy, momentum, and velocity, moving at the maximum speed allowed by the laws of physics while carrying information and energy across the universe. Finally, the zero rest mass property of photons illustrates why light behaves differently from hypothetical particles with mass attempting to reach light speed. No amount of energy will ever propel a massive object to c. It is fundamentally forbidden by relativity. Photons, by contrast, are not limited in this way. Their massless nature, combined with momentum, allows them to traverse the cosmos unimpeded at the exact speed that defines the universal limit for motion. This distinction is central to understanding why light, and not any conventional particle, can achieve what otherwise seems impossible. In summary, Photons can travel at light speed precisely because they have zero rest mass. This allows them to move without experiencing time, avoids the requirement for infinite energy, and ensures that information and energy can propagate across the universe at the cosmic speed limit. Their existence embodies the ultimate principle of relativity. Massless particles move at c, massive ones cannot, and space-time itself enforces the separation. It is the elegant solution nature provides to reconcile motion, energy, and causality across the vast scales of the cosmos. As we reach the culmination of this journey through relativistic physics, it is worth stepping back to appreciate the bigger picture. The exploration of what would happen if one could travel at the speed of light, while fundamentally impossible for objects with mass, is far more than a theoretical exercise. It is a lens through which we can re-examine the nature of time, space, energy, and the universe itself. Each segment we have explored, from time dilation and length contraction to causality breakdown, cosmic horizons, and the behavior of photons, offers a window into the deep, elegant structure of reality that governs everything around us. Humans cannot travel at light speed. The laws of physics make this an absolute constraint. The mass of any object increases toward infinity as it approaches c, and the energy required to reach light speed likewise approaches infinity. Biological organisms could not survive the forces, radiation, or particle impacts encountered at such velocities. Communication with Earth becomes impossible as time dilation and relativistic Doppler effects distort signals. Even hypothetically, causality itself forbids the traversal of this ultimate speed limit. Yet, these impossibilities are not limitations of imagination, they are the universe's way of preserving coherence. The cosmic speed limit exists not as an arbitrary rule but as a safeguard for the structure of spacetime, ensuring that cause and effect remain consistent and that energy and momentum are conserved. Understanding these constraints reshapes our perception of time and space. Time is no longer a universal, unchanging river. It is malleable, dependent on relative motion. A traveler moving near light speed experiences years or decades while millennia or billions of years pass elsewhere. Distances contract along the direction of travel, transforming the vast, unbridgeable expanses of the cosmos into scales manageable within a human lifetime, at least from the traveler's perspective. Space itself is flexible, a dynamic arena that bends and stretches with motion. Even light, which travels at the universal speed limit, demonstrates the profound interplay between time, energy, and the geometry of spacetime. Photons traverse the universe timelessly, unaffected by the energy constraints that bind massive objects, highlighting the elegance of relativistic physics in mediating the limits of reality. Relativity also challenges our intuitive notions of simultaneity, motion, and causality. Two observers moving at different velocities may disagree on the sequence of events, on which events are simultaneous, and even on the duration of processes. This relativity of experience is not a quirk, it is a fundamental aspect of reality. It emphasizes that our everyday perceptions, built under conditions of low speed and weak gravitational effects, represent only a tiny corner of the full cosmic truth. Exploring near-light speed scenarios expands our mental horizon, allowing us to grasp that time, space, and motion are deeply interconnected and that our human-scale intuitions are not universally applicable. The study of relativistic effects also inspires technological and scientific insight. Particle accelerators, for instance, routinely push subatomic particles to speeds extremely close to that of light, confirming the predictions of special relativity with extraordinary precision. Observations of cosmic rays, relativistic jets from black holes, and gravitational lensing provide additional experimental evidence of these principles in action across the universe. Each discovery reinforces the idea that the laws of physics, though sometimes counterintuitive, are consistent and profoundly predictive. They allow humanity to understand phenomena that span billions of years, trillions of kilometers, and energies beyond ordinary comprehension. Moreover, these insights have philosophical and existential implications. Time dilation, cosmic horizons, and the behavior of light challenge our concepts of longevity, exploration, and human presence in the universe. The traveler at near-light speed can witness the vast scale of the cosmos in a lifetime, yet must reconcile with the isolation that relativistic motion imposes. Civilizations on Earth continue, generations pass, and the universe evolves, largely unobserved by the traveler. The disparity between subjective and external time compels us to rethink our relationship with the cosmos, highlighting both the potential and the limits of interstellar exploration. Finally, contemplating the speed of light and its implications deepens our appreciation for the elegance and coherence of the universe. Every restriction, every impossibility, is a testament to the underlying order that governs matter, energy, and information. Photons glide across billions of light-years carrying energy and information, while massive objects remain bound by the cosmic speed limit. Time stretches and compresses, space warps, and distances contract, all according to precise, beautiful mathematical laws. By understanding these phenomena, we gain not just practical knowledge but also a sense of or at the profound structure of reality. In conclusion, while humans may never ride a beam of light or traverse intergalactic distances within an instant, studying the physics of near-light speed travel transforms how we perceive the universe. It teaches us that time is flexible, space is dynamic, energy is conserved with precision, and the cosmos operates according to deeply interwoven rules. Relativity challenges our intuitions, stretches our imagination, and ultimately reshapes our worldview. The impossibility of light-speed travel does not limit our understanding. It enriches it, revealing the remarkable elegance and coherence of the universe and inspiring humanity to explore, comprehend, and marvel at the cosmic tapestry in which we exist. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.